getting our newsletter and you'd like to get our newsletter, there's a thing back there to sign up for it. If you think you would like to be a member in 2026 and you're not a member now, there's a membership form back there. And you can also join very easily online. So we will have one more program this year. It's going to be the second Tuesday in November, which is the 11th. And it's going to be Lisa K. Wagner. She's a plant ecologist who was with the South Carolina, the Botanical Garden at Clemson University for 20 years. Her husband is Tim Spira, who a lot of people know, and they both are well known for their concentration on working with plant communities when you're building landscapes or putting natives in your garden. And so that will be the topic. It'll be creating an ecologically sustainable landscape. And that will be the final event for BRNN in 2025. Thank goodness. One other I'd like you to know about is that Wednesday, November 5th, the first Wednesday in November, the Sierra Club is going to have an interesting meeting in this same place and also on Zoom. And they're going to have Lisa Raleigh, who's the executive director of RiverLink, talking very expansively about the status of our rivers and restoration and how to work, how to build back right when you're building back in a flood area and a lot of different topics. So try to make that if you can. We'll take questions. It's Jake's choice whether he takes them during the talk or after the talk, but you're going to need this microphone to ask them because we do have people on Zoom, and if we don't speak into mics, they don't hear what we say, and they get very irritated. So, and for those who are on Zoom, if you have questions, please put them in the chat, and then I'll convey them. So, let me introduce our speaker. Jake Hagendorn is an assistant professor of environmental science right here at UNCA. He's had a long day of teaching in labs today. His courses include soil science, energy and society, and agriculture. And his research goes into a lot of areas that are the interface between agriculture and soil, sequestration, carbon sequestration, and climate mitigation. His doctorate is from the University of Maryland Center for Environmental Science. And tonight we're going to benefit from his experience.
Thank you, Matt. All right. Can y'all hear me okay? The mic is working? Okay, awesome. Let me check now the slide advancer here. Yeah, do we know if we can? Hey, Mackenzie, can we turn off the light right above the projector? All right, perfect. That's really great. That's awesome. And this is working. Okay. All right, y'all. Well, thank you for inviting me. My talk is Mitigating Climate Change Using Science to Transform Uncertainty into Progress. Like Mayo said, I'm Jake Hagendorn. I'm going to tell you a little bit about my story here, just so you it's related to some of the people in the room, but also just for us to find connection between each other, maybe based on some of the things I've done. The other thing I'll say to set up this talk is I will take questions throughout. So if you have a question, let's go ahead and ask it and get it answered. That might delay us, but that's okay because we're at least talking to each other. All right. So we can't see that top line, which might be an issue for future figures. See if we can press OK. Okay, so I grew up in Brevard, and then I went to UNCA. Kitty was my professor from my Environmental 130 class, my intro, Dr. Reynolds. That's right. And so went to UNC Asheville Environmental Studies Department and immediately after that, that's where I developed my love for science and my love for teaching, honestly, was starting here. After a year after that, I went to Sri Lanka through the Fulbright program to teach English with my partner, Annalise. So we taught English in Sri Lanka to a middle school, a Buddhist middle school girls. And so that was a really good experience, soft diplomacy. Then I went to my master's degree at Penn State and worked on my master's is in geosciences, but my project was looking at a wastewater reuse system and kind of how effective that has been for the longevity of the project. And then I did my PhD at the University of Maryland, which is a Center for Environmental Science, which is a series of 5 labs kind of around the main campus. And so if anyone's been to Western Maryland before, any Western Marylanders, Frostburg, Cumberland, Hagerstown, in that area, in Frostburg was where the lab is that I worked in. So I did my PhD there, specifically looking at greenhouse gas emissions coming out of soil as a result of different agricultural practices. So I worked with farmers quite a bit to look at how do their management systems impact how many greenhouse gases are produced or consumed via those practices. I then taught for a year at Warren Wilson and then made my way back here about 3 or 4 years ago now at this point. So glad to be here. Probably have to click on it again, don't I? Don't I, Mackenzie? Okay. Okay. So we're going to talk about climate change. I am probably you're all aware of climate change fundamentals. I'm not here to necessarily convince you. I'm here to practice or to give you additional practice in how to talk about it, particularly in the context of what we would say attack on climate science. All right. And so we're going to kind of review some of those fundamentals just to kind of give you those tools to be able to talk about it confidently and effectively. All right. So I like to show this one with my students often. And so what is climate change? What controls climate? It's essentially just an energy balance on Earth, right? Energy's coming in, energy's going out, energy's being absorbed. We're just trying to track how does that energy change over time. And so there are multiple factors that go into the energy balance: anthropogenic human factors and non-anthropogenic non-human factors, right? So we're going to look at these. This essentially what's going to happen is there are going to be a series of lines that go across here over time, and those lines are going to be labeled. So I want you to watch those labels, and I'll kind of narrate them as it happens. All right. So the first one is this is the observed temperatures that we've had on Earth. From about 1880 to kind of mid 2000s. This is observed temperatures. You can see it was kind of steady and then it rose. So we're trying to figure out what's doing that. Well, orbital changes, right? As we orbit around the sun, that orbit is not constant. It does change. We also tilt and we wobble a little bit. And that's going to change how the temperature, how much energy comes to Earth. But that line didn't match the observed. The sun is changing sizes, right? The sun is growing currently, and we have to track that if the sun were to grow, that would change how much energy we come on Earth. But that line didn't match the observed. Volcanic emissions, certainly in the past, volcanic emissions have driven climate change prior to humans being here, 100%. But current climate change, that volcanic line does not match what we see, what we observe. So if we look at all of these natural factors that certainly have driven climate change on Earth in the past, if we look at all of those factors, all of those are not really matching what we're actually observing, right? And it's important to note this because you're going to see people argue currently in today's media that it's natural factors that are driving climate change. But you can see those weren't matching our observed temperatures. But now we can think about more anthropogenic. This is land use. Land use does change climate, but you can see that land use, while we have examples at smaller scale, we don't see it matching the observed. Let's look at change in ozone. Ozone has led to a little bit of an explanation of the observed line, but not the whole thing. Aerosols. Aerosols are a funny little thing. They're actually going to cool the climate. And you can see here, they're going to contribute to climate cooling. We need to track those. We need to understand how those work. So we measure them. And then we have greenhouse gases. And you can see here that the greenhouse gases actually are a little bit above, but certainly follow the trajectory of the observed temperature. And so if we factor all those in, land use, ozone, aerosols, greenhouse gases, and greenhouse gases are mostly derived from fossil fuel burning. If we add all those together, those anthropogenic sources, we see that the human factors are pretty closely following the trajectory of the observed temperature change. And so we know, though, that climate is a mixture of human and non-human. And so we can throw all of those together, look at all of our forcings and all of our observed. And what we see is that a pretty close match. So we're pretty confident because we've actually measured those natural and the anthropogenic. We have the confidence when we match this. All right. Okay. So those are fundamental climate changes. There are natural factors. They do have an impact, not within the scale and the time frame that we've seen in the past 100 years. Okay. All right. So we're going to talk about greenhouse gases. I mentioned those. I just want to refresh you on that. So greenhouse gases are essentially just different molecules. Examples: carbon dioxide, nitrous oxide, methane. I'll show you a few of those in a second. But essentially, those greenhouse gases contribute to the greenhouse gas effect, which essentially says that as energy and comes into Earth, Earth absorbs that energy and re-radiates it out as infrared energy. All right, and then it leaves. On its way out, those greenhouse gases that are in our atmosphere, those particular molecular structures get excited by that infrared energy. And when they get excited, they vibrate. And when they vibrate, they trap that energy on Earth. All right. And so essentially, without greenhouse gases, we would be cold. We have to have some greenhouse gases. That's what's allowed the temperature to be warm enough for human existence, for life on Earth. But we are seeing too much greenhouse gas, too many greenhouse gases, leading to excessive warming. Okay, so that's the greenhouse gas effect. Energy coming in, infrared energy going out, exciting those greenhouse gases, trapping that energy. Okay, so let's, everyone, even on Zoom, everyone take a deep breath in through the nose and out through the mouth. Okay, so you took that deep breath. What did you actually breathe in? So if you look up at this graph on the right here, you can see that what you actually breathed in was about 78% dinitrogen, 21% oxygen, and then a super small fraction, right, of these other gases. All right. So most of what you breathed in is not a concern from a greenhouse gas perspective at all. We're not concerned about dinitrogen. It's not a greenhouse gas. Oxygen, I'm glad we breathe that in, right? We use oxygen to live for cellular reproduction, for energy, right? But look at this small fraction here. This is a super small fraction of our atmosphere. And of that super small fraction, it's dominated by CO2. And then you have some methane, and then you also have some N2O in there, an even small fraction, another type of greenhouse gas. Anyone been to the dentist? Maybe gone with the laughing gas, the nitrous oxide mask? Maybe? That N2O, that is a type of greenhouse gas, okay? So what I want you to note here is that without greenhouse gases, it'd be too cold. But with too many greenhouse gases, we're going into too warm. But I want you to remember that the amount of greenhouse gases in our atmosphere are super small. And that's important because that means we can actually impact it. There's really nothing that we can do to impact 78% of our atmosphere of nitrogen. We pull nitrogen out of the air to create fertilizer for agriculture all the time, every day, 24/7. We're pulling that nitrogen out of the air to make that fertilizer, but it's not changing the percentage of the atmosphere because it's such a large mass. But such a small amount of greenhouse gas means that we as humans, our actions can actually impact its concentration. All right. So I want you to think about the things in your own life that are relatively small quantities, but changes to those can have large impacts because that's what greenhouse gases are on Earth. Small quantity, but a change that can have a large impact. Okay, so I forgot to tell y'all what I formally define myself as, which is a soil biogeochemist. And so I wouldn't be a biogeochemist if I didn't show you the global carbon cycle. This is like grained into me. I have to think about the carbon cycle, right? And so I want you to note here, there are two different things. There's arrows and then there's circles, right? Arrows are flows or fluxes, and circles are pools. Okay. And so essentially, this global carbon cycle, and I know we're focusing on carbon right now, that's okay. You can see how there are fossil fuel pools, and then there's a fossil fuel flow based on combustion of those fossil fuels. You can see here that, look at this big green dot. Thank you, ocean. Ocean holds a lot of carbon, right? And then there's some flux out and into the ocean, right? There's some flux from the atmosphere into the ocean, right? Here you can see I'm a soil biogeochemist, so I'm going to care about these soils. These soils have a pretty large portion of carbon in them, but you can see there's vegetation in, and then there's vegetation going into the soil, and then there's decomposition going out. But overall, there is actually an increase of flow going into the soil in the permafrost. And then you can see in the atmosphere here, you can see that the atmosphere, that's the size of the pool in the atmosphere. And if we add all of these arrows up, both the ones going in and the ones going out, we end up with a positive increase in the atmosphere of about 5.2. All right. So I show this graphic to note, so that you can note that which are the biggest arrows, which are the biggest dots, pools, but then to say that the atmospheric concentration of CO2 is rising after you account for all of these. Okay. So go ahead.
Result of the burning of fossil fuels.
That's right. So yeah, so that's a great question. Great question to think about here is that how do we get to that 5.2? Essentially, this 9.6 is mostly human anthropogenic flow into the atmosphere. Half of that 9.6, roughly, half of that 9.6 is being absorbed in excess by vegetation and the ocean. And so essentially the earth via vegetation and via the ocean is kind of buffering about half of our impact. All right. And I show you that in this graphic as well. So here you can see the concentration just kind of like in a different manner. I know this can get a little busy, different pools and flows. This is a little more simple graphic here. This is the concentration of CO2 in the atmosphere in 1850. When all of the coal burning we've done, we've essentially added 105, all of the oil, all of the gas, these three fossil fuels here. Cement, actually a pretty big player that it gets its own thing over here. And then land use change, all right, has been a big, an impact on CO2 concentration in our atmosphere. But then we can think about that is all of the impacts that have added CO2 to our atmosphere. And we should be around 600 right about now, but we're not. And the reason we're not is because we have land sinks via vegetation and permafrost and soils that are sequestering some of that. We have an ocean sink as well that is taking in a lot of that carbon. So we end up at about right now, about 420 parts per million of the concentration of CO2 in the atmosphere. And so we can be thankful for the land and the ocean for a kind of buffering how bad it could be, right? But there are limits to how much the land and the ocean can absorb. And they can't absorb at the same rate that they have been forever. There are biophysical limits to that. So that's where you get from 1850 to about now, about 420. So that's where all of it's gone. All right, so where are we going? Talked about kind of the past, what has happened. What are the projections going forward? Well, here on the graph, you can see time and global CO2 emissions. Now, note this is global. I'm going to show you a US-centric graph in a second, but note this is global. And you can see the red dot is where we are right now. And essentially, these are just different models based on different actions we can take that project forward what global CO2 emissions could look like. And these are just a variety of different scenarios. Go ahead. Yeah. That's right. Yep. Yep. Great question. Yeah, I love that question. So essentially, yes, we are right now and have been since about 2010 decreasing this coal amount, but we've been replacing it with the gas. And so globally, in the US, we've been replacing with gas as well, but the gas burns cleaner, less CO2 emitted upon combustion than the coal. So overall in the US, we've seen a reduction in greenhouse gases, and I'll show you how much of a reduction. We've seen a reduction in greenhouse gases as a result of the switch from coal to gas. So, yep, good point. Yep. Okay, so I was gonna try to get the way. Okay, so here we go. So these are future projections. Okay, and you can see they're super variable, right? We're talking about doubling our CO2 emissions, possibly soon if we choose this scenario. We're talking about getting to net zero if we choose any of these scenarios, maybe by the turn of the century, right? So it's super variable. It depends on the actions we take, and that's what we're going to talk about today is those actions, okay, and how they derive some of these. Another way of looking this is looking at just temperature, and I like this graphic because of the color, right? Colder is blue, warmer is red. But look at these different scenarios on the right side here. You can see that this is today, and I want you to take note of this legend, which might be a little difficult to read, but you have this curved arrow, which is peaking our emissions. This half line, which is halving our emissions, and then this zero line, which is getting to net zero. Net zero meaning we haven't cut emissions to zero. We are just emitting no more than we are also absorbing back onto the land and the ocean. All right, so it's just a net zero. But when we do that is going to control the essentially the severity of the temperature increase, the degree of the red, right? And so you can look at these two scenarios. If we were to peak now and we were to half here and get to net zero here, from today, right, it's going to be warmer. Best case scenario, right? Peak now, half, zero. It's going to be warmer than it is right now, right? Okay. So let's look at this scenario. We peak now, but we can't half until 2050-ish. And then we get to net zero maybe in 2080. You can see the degree of the red. Generally, I don't like to think about these three up here. I like to think that we can do something like these, at least the two. I like to think we can do these bottom three. And I think I'll show you probably some trajectories that show us possibly being able to actually realistically get there. All right. Despite a lot of the uncertainty. Okay. So what is an increasing temperature going to mean? Increasing temperature is going to lead to a climate that's going to be have a higher probability for extreme weather events and a higher probability of more intense extreme weather events. So this is kind of a theoretical graphic, but here you can see on the y-axis you have less probable, more probable, cooler, warmer. And what I want you to see here is essentially that if we think about a pre-industrial climate here, right, we can move up on this graphic, and that just essentially means that the extreme weather event is going to be more probable. We can also move to the right, which means that the probability can stay the same, but the intensity of the event increases. And what we're going to likely see is kind of a diagonal here, where both the probability of the intensity and the probability of the event increases as well. Okay. So this is just kind of a theoretical to show that. And the reason that's important is because that means that we need to prepare for, and we need to create systems for accommodating and understanding that there's going to be loss of life, property, and community. So how are we going to adapt to that? Right? We need to create systems so we know this is going to happen. We've seen it already happen. How are we going to adapt to that? It's also going to add more uncertainty into energy markets, trade, agriculture. All of these extreme weather events also impact all of these types of markets. So another graphic, this graphic has since, it has not been removed from the NOAA website, but it has said that it will no longer be updated. So thankfully I got a screenshot of it before it got taken down. But here are the United States billion-dollar disaster events from 1980 to 2024, and adjusted for inflation. And what you can see here is the different colors align with different types of events: freezes, flooding, wildfire, drought, severe storms, tropical storms, all of that. But you can see visually here that, again, this accounts for inflation, that we've seen a lot more costs because of extreme weather events, a lot more cost to us. So this is really an economic problem, or can be presented as an economic problem. And in a lot of circles, it probably is better presented as an economic problem. And this kind of gives you the tools to do that, right? Of course, it's not just economics. It's also, there's life in here, human life, that of course is extremely important, but essentially we can put it in cost economic terms. Okay, so I'm going to challenge y'all with a little tech, okay? A little bit of tech. I want you to get your phones out. I want you to try to look, scan this QR code. This is an app that was developed by a colleague of mine, former professor, now colleague of mine, to kind of try to give you a sense of what the temperature is going to feel like in 60 years, right? And so take a picture of this. And essentially how it works is, I'll show you some examples. You just select a city that you want to know what it's going to feel like in 60 years, and it's going to tell you an analogous city that exists right now of what the city you selected will feel like in the future. So I'll give you an example, and I have the QR code on every page. So if you want to keep scanning it, keep going for it. So here we have Asheville, right? Asheville in 60 years is likely going to feel like Rome, Georgia. Some of y'all might be like, I've been to Rome. It's okay, right? Maybe, I don't know, right? But that's a temperature increase, right? I've had people react different ways. So Asheville is going to feel like Rome. Here we go, Charlotte. Going to feel like Houston. So we get a drastic difference here. Anyone, why do we think that is? Why do we think Asheville might not be having as drastic a difference as Charlotte to Houston? Elevation, you got it, 100%. So elevation, mountains are going to help buffer some of that temperature change and that precipitation change that are going to essentially result in a slightly less of a field change compared from Charlotte to Houston. And so feel free, y'all. I got another example. Jacksonville, Florida. I've been down there. Going to feel like central Mexico, north of Mexico City. Oof. All right. And so feel free to select any city you want. This has been updated now to go international. At first, it was just kind of bound to North America. Now it's even gone international. I had one student going through this, and they were like clicking every city, and they found I forget the city, but they found a city that had no someone go to Sri Lanka. Someone go to Colombo, Sri Lanka, off the coast of India. See if that one has an a city that it can be compared to. And let me know what you find. I think that might have been it. Colombo. It's on the east coast of the small island. There you go. So that was the one that my student checked out. So Colombo, that's where I spent a year in Sri Lanka, right? I spent a year in Colombo, and when my student clicked on that, I was like, wow, that there is no analogous thing on Earth currently for what that climate's going to feel like. So I give you this tool. It's kind of a shock and awe thing, but also I want you to use this tool because like the more we can talk about this, the more we can spread the word to our friends about, hey, these are kind of some cool tech things that you can use to kind of see what future is going to look like. I think it makes it seem, the more we talk about it, the more it's just on the back of our minds. So this was on an intermediate path. This was on an intermediate path. Yep. Okay. So one other thing I wanted to show was just a shift kind of with these temperature moisture regime changes. We're going to expect and are seeing a shift in plant hardiness zones. So you can see here, like we are in zone 6 right now on the edge of zone 6 and 7. We're going to firmly move into a 7 as time progresses. Okay, so let's think about some mitigation. Some climate mitigation. I'm going to kind of frame it about what mitigation is and frame it within the context of like priorities of where to mitigate. Essentially, what is the low-hanging fruit of mitigation? And then we'll get into some specific strategies. All right, so we have two terms, mitigation and adaptation, slightly different. Mitigation is reducing the amount of greenhouse gases to limit climate change severity. So this is consuming less fossil fuels, increasing renewable energy production, changing transportation systems, regrowing forests, becoming more energy efficient in our technologies. Adaptation is learning to live with the climate change that's already happened and that will continue to happen. That can look like infrastructure improvements. That can look like crop modifications for climates where that are going to be more adaptable for growing food, right? Trying to figure out how to modify those crops to survive in future climates. A lot of early warning systems, particularly when we think about extreme weather events, trying to figure out more early warning systems. And then managed retreat, right? If we think about the Colombo, Sri Lanka example, there's no analogous city on Earth right now of what it's going to feel like. There are so many lower lying areas that will have managed retreat because of sea level rise. Sri Lanka was one example where they already have agreements with Australia for managed retreat as sea level does rise. I think we're going to start to see more of those, and we're going to need to see more of those agreements between countries start to have those conversations now, so that when the time comes, we're prepared. Of course, these two are connected, mitigation and adaptation. To kind of think about a framework for mitigation, I'm going to mostly talk about mitigation rather than adaptation. A framework for mitigation is kind of like the whole reduce, reuse, recycle thing, but a little bit different. I think it's avoid, reduce, replace, and offset. All right. Avoid is just getting to reducing the amount of fossil fuels greenhouse gases we have. Reducing them is consuming less. Replacing is going to be opting for like a more energy efficient tool or system. And then offset is essentially saying I'm going to try to like buy some offsets. We see this with a lot of larger companies that can maybe advertise that they have gone carbon neutral or net negative, and they're maybe buying carbon offset credits globally or domestically. So those are kind of offset credits that exist. But in terms of what is the priority, avoid, then reduce, then replace. Offset's kind of the last thing. And so here's a snapshot. I haven't showed this graph to you yet, but here's a little snapshot of the current greenhouse gas situation in the US. And so note that it's just the US. You can see here we have different colored sections that are changing in thickness. And this is emissions of carbon dioxide, and this is time. We have different sectors, sources and sinks here. Sink is below 0, that have different thicknesses. And you brought up the coal to natural gas, which I'm glad you did. I'll show you another graphic in a second. But you can see that the three largest emissions are industry, electricity, and transportation. So when we think about what are the things we should change first because we have the most potential to make a big change, it's got to be one of those three, right? Residential, commercial, agriculture as a whole are maybe industry, right? Not saying we shouldn't try to change some of these to reduce emissions. We're just saying that these are the big players, that if we make a slight change to these, we can make a big change to the whole thing, all right? And so you can see here that we have peaked our emissions in about 2008, 2010, and we've had a slow decline. Most of that is because of our transition from coal to natural gas, and I'll explain that in a second. But notice here that the electricity generation has decreased in thickness relative to 2006. Transportation has increased slightly. And all these other categories have stayed relatively same. It's been mostly electricity generation going down. How do we compare to the world? So here you can see us, again, carbon emissions, time. Here's the US, Russia, Japan, China, EU, the world average, and then India. We're up here, and let's look at this graph we started in the 90s. You can see that here in the 90s, we saw a slight increase up until 2008, and then we've seen a pretty good decrease. Pretty good, but still much higher than the rest of the world. So although the story is that we have decreased, and that's positive, the rate of our decrease needs to happen more quickly for us to be on par with the rest of the world. This is everything. This is transportation. Yeah, so the question was, is this just driven by transportation or a particular sector? No, this was all sectors. This was just to say that, just to give you an idea that we had this peak and then this drop, and I wanted to show that within the context of the entire world. So we have a peak and a drop, and you can see that with other countries, though, even though we had this drop, which is great, we're still higher than everyone else. So we have a ways to go. So how are we going to get there? How are we going to get there? Here's some examples of how we have gotten to where we are and how I think we're going to continue to go down that road. Declining coal. First one is declining coal. You can see here on this graphic, since 2008, look at this brown here. This is billion kilowatt hours. Don't worry about the unit. Doesn't really matter. It's more about the relative comparison to the different colors. But here you can see coal increased and then coal has decreased. And so the thickness of that line has shrunk way down. And what has replaced it is the increase in thickness of natural gas. So that blue line has increased in thickness as the coal thickness has decreased. You can see overall we have kind of plateaued our electricity generation. All right. We've increased in renewables quite a bit. I'll explain that story, but we've increased in renewables, but we've switched from coal to natural gas. Positive, of course, is that the positive is that one unit of coal produces twice the greenhouse gases of natural gas. So natural gas is a cleaner. It is not clean, but a cleaner source of electricity. And most of this natural gas has come from hydraulic fracturing. So switch from coal to gas. Another one, increasing renewables. So here we see same graphic, but just looking at renewables, solar, wind, geothermal, biomass, hydroelectric. You can see here since 2010-ish, wind is crushing it. Wind's going. And solar has picked up recently, like since about 2016. Solar's really picked up. Hydro's remained steady, even dropped a little bit. But wind takes the prize in terms of electricity production in the US for renewables. Where is that happening? Iowa, Texas, California. So this is for solar and wind in 2023, but the same trend is this year as well. Texas, Iowa, and California. And we might be thinking, this is a pretty blue state. And these are not so blue states, right? Stereotypically, right? There's a lot of renewable energy going on in Texas and Iowa. Yeah. Why? It's a moneymaker. It's a moneymaker. If it makes money, it's going in. All right. And wind in Iowa and Texas and in other places, I'll show you in a second, makes money. Making money in our system is going to win. So that's what's kind of happening right now. If we look at new utility scale, so this is specific utility scale, not residential installation, but utility scale, big structural change, utility scale generation. Look at this, how this has changed over time. You can see that in 2000 to 2010, dominated by natural gas. Those are the things coming online were natural gas. But since 2015, the new electricity generation has been solar, battery, and wind. That's through lots of changes in different administrations here, right? Lots of different Congresses. And notice how solar has really ticked up. New electricity generation is going up. Battery storage, wind, a little bit of nuclear here in the past couple of years because of a plant in Georgia. But so that one's good to see from a renewable increase perspective. All right, another example of a successful mitigation strategy, the Inflation Reduction Act. Now this has since been stripped and modified, and I'll talk about a couple of those details in a second. But essentially, the Inflation Reduction Act passed in 2022 threw a lot of money at these renewable projects. Both residential, utility scale, honestly, mostly utility scale, less so on the residential. And so here you have clean energy tax credits, clean energy incentives, clean fuel and vehicle changes, air pollution money, lots of money thrown at this, and it did have a significant impact on reducing our greenhouse gas emissions. From our personal perspective, it lot to do with heat pumps, home energy upgrades, wood stoves, biomass stoves, water heaters, a lot of tax credits for that. Some of y'all maybe took advantage of some of those credits. Many of those residential credits are phasing out this year into next, but a lot of those utility scale credits are actually staying for a few years because those projects, again, are going to make people money. A lot of those weren't cut from in the One Big Beautiful Bill Act down here. All right. That's the OBBBA. So another thing that wasn't cut here, the zero emission nuclear. That was not cut. That remained in the 2025 bill. All right. Other things that remained, a lot of solar battery installation. All right. A lot of that battery installation money remained. It was not pulled. And that's because many of the utility companies were pressuring Congress to say, we've already planned for these new energy installations. We've already committed money to them. We need somewhere to put that energy. We need that battery storage. So it stayed in there. All right. Yeah, so a lot, yep. Go ahead.
The question is really, you're talking about building larger battery storage facilities? Is that what you're?
That's right. Yep. And so that would be two things. We can think about, y'all have probably heard in the news, like AI data centers needing their own power plants. They also are using battery storage at those power plants. Existing power plants, like even at Lake Julian, Duke is planning to add a battery system even to Lake Julian, has started that. And so that's essentially just saying we're going to produce that electricity, then we want to store it in these battery systems so that we have more capability of dealing with grid changes over time. And we can deal with the highs when we need excess energy. So some of these things have remained, all right? But of course, if we look at this, we can see what did the Inflation Reduction Act, when we projected out how much of an impact it would have in our total greenhouse gases. If our goal is net zero, which is to get to a zero mark, right? The IRA are different projections for the Inflation Reduction Act. And you can see that again, we are decreasing our emissions, right? The IRA was projected to continue that decrease at this rate till about 2035 here, right? Without the IRA, now we're looking at still a decrease, but that decrease is not as great. Okay, so we still have a decrease, but that decrease is not as great. And essentially, both of the bills, the IRA and the OBBA here, really only projected out to 2050 or 2035. Some other independent people have projected out to 2050, but the intent was that these would be updated before then to continue this decline even more steeply. So what you can see here is that IRA, no IRA, we're still decreasing, but the IRA is going to decrease it even more at a steeper rate. Either way, though, we weren't going to get to net zero by 2035. I don't think we ever had a chance at doing that, but you can see, though, we need to do a lot more work to get to net zero, certainly by 2050 or 2100. So what can we do? What can we do? I tell my students that we could wait around for a big silver bullet, but it's probably not coming. All right. And so people think about like nuclear fusion, right, as a potential silver bullet. Yeah, but we've been working on that for about 50 years. And so it's still got a way to go to be applicable in our society. So there's likely not going to be a big technological breakthrough, and it's going to be small increments using existing technologies. So I like to use this graphic to kind of frame those mitigation strategies and the potential for those strategies to how much of an impact they can have. And so this is near and dear to my heart, soil carbon sequestration. I show this a lot with my soil science students. So we know what is the maximal biophysical potential is for carbon to be absorbed in the soil. But then we have to think about what is actually physically possible. What management things can we actually do to make that happen? Then we have to say, well, what is economically possible? Of course, economics change, right? But what is economically possible? And then what is politically and socially achievable? All right. And so that's going to kind of frame how much we can actually make with a particular action or mitigation strategy. And these are all realistic, right? These are all realistic in the sense that we have to account for those, but scientists do that, right? So future mitigation option one, continue solar and wind. Just keep going with that. That has worked in the past 8 years. Continue going with that. So this graphic shows, I want you to keep an eye over here. I want you to keep on the scale of the bar or the size of the bar, the length of the bar, and then the color. The longer the bar, the more potential there is to reduce emissions. with that particular technology. The color of the bar, blue or red, is the costs it takes to implement that. So you can see solar and wind, really low costs, and we can get up to 2 to 3 at really low cost. We can get 2 to 3 gigatons of carbon reduced with solar and wind. So in terms of low-hanging fruit, that's it, right? That's it, solar and wind. Some reduced methane from coal here is pretty cheap for us to do, right? But those are the three things, cheap to do and make a big difference. Let's look at this one, getting into agriculture. So let's get out of the electricity game. Let's get into agriculture. You can see no blue. No blue. There's going to be costs, higher costs associated with any agricultural changes to reduce greenhouse gas emissions. But if we look at the ones that are going to be the most impactful, the length of the line, we have reduced conversion of natural ecosystems, so land use change, right? And we can think about restoring wetlands, restoring ecosystems. Those also are going to contribute to this. Carbon sequestration in agriculture. My student is in the back, Ian. He is currently doing an undergraduate research project right now looking at carbon sequestration at farms in the area. And so feel free to talk to him after. And so carbon sequestration, right, has a lot of potential, but the costs are higher. Okay. Say it again.
Does that happen?
You've asked, how does that happen? How do the costs go higher?
Oh, but what is carbons?
That's a great question. Yeah, so I'll show you. But essentially, carbon sequestration is just saying any action you can take by a farmer or by a policy where you are trying to increase the amount of carbon that is being pulled from the atmosphere via vegetation, for example, into the soil. That's going to be sequestering that carbon, pulling it out of the atmosphere. Vegetation does that for us. We don't have to do anything. Vegetation, growing things does that for us. And so within agriculture, there are different types of management strategies that you can do to keep things growing in the soil, but then also to keep as much carbon that is whatever you're pulling off to harvest, only pull off what we need to do our food or our grain, leave everything else in the soil. And I'll give you a few more examples. Okay, so we think about agriculture here. Another graph for you. Area of practice. Okay, so this is the area of adaptation. So this is a larger area. And this is the reduction or removal rates that could happen, the removal of greenhouse gases. And so I want to point a couple of things out to you. Look at this one right here. This says restore histosols. Histosols, think of wetlands. Okay, think of wetland environments. Think about the Everglades. Think about like some areas around like northern Minnesota, Michigan, a lot of wetland areas. Okay, here, if we were to focus on restoring wetlands, that's a really small area, but the rate of removal is huge, right? And so restoring those wetlands, which were probably impacted by agricultural land use or draining them for arable land is one example, is kind of a priority, I would say, within agriculture. The next thing you can get into is thinking about like biochar. Anyone been down to Mills River and seen the stump dump that's been burning on fire? Okay, so you talk about some production of some biochar right now. The stump dump down in Mills River right next to the Angles caught on fire last week. And it's still on fire. But you're producing some biochar in there. Biochar can be applied. That's essentially just carbon in kind of a more what we call recalcitrant or difficult to break down form that gets applied to agricultural land. And that could sequester. And last one is thinking about cropland. I actually have another example. I'll give it here. So other agricultural practices that are important, I mentioned biochar, reducing tillage, cover crops. This gets into pulling that carbon out of the atmosphere. If you can keep something growing on the land, even if it's not something that you're selling for production or for income, you're just capturing more carbon into that soil. And that's going to help with sequestration. So cover crops, agroforestry, organic amendments, land restoration, all of these practices, and these are the practices that I research as to like their degree of carbon sequestration potential. All of these practices can improve it. The degree of their improvement, I think, is what Ian is asking, is how much will it actually improve? Can we measure that? And that's what we're researching now. Okay, so I'm gonna finish up. I'm a couple minutes over. Getting to net zero. So here, just to revisit this graph, we have different sectors that have essentially are kind of saying that the electricity generation sector is something that we should focus on. Transportation, industry, those are the big players. And big changes are small changes to those can make a big change. So one group out of Berkeley looked at some tangible actions we can take that will get us to net zero. And here, if we take these 8 actions by 2030, which I know is not that far away, but if we were to do these 8 actions, this would get us to net zero by 2050. And I want you to just look at the first 6. Solar and wind. Solar and wind. Expand it. Bigger and bigger. Eliminate most electricity generation from coal. Don't do anything different. Coal's declining. Keep it declining, right? It's continuing to decline. Maintain natural gas. It's an interesting, but that's what they suggest is maintain the current natural gas. And that's going to be the emissions that we're going to try to offset with other practices to get to net zero. Increase zero emissions, EVs essentially to 50%. Heat pumps. Heat pumps are a big one. Increase those to 50%. Those have been expanding more. I have a side gig of building houses, small houses. And so I've installed lots of heat pumps. And so I'm all about the heat pump. Talk to you about heat pumps all day long. But yes, heat pumps are becoming more and more popular. Geothermal air source heat pumps. And then new building energy efficiency goals. So those 6 things, and I can touch on the other 2 later if you want, but those 6 things, if we were to do those, we could get to net zero, according to the models on this group. Those seem achievable in the sense that they are not relying on a silver bullet technology that we know we don't have. They're relying on technologies that we already know we can do and that we already have done. We just need to continue doing. Okay. I'm a couple minutes over, but I was thinking, where does a naturalist fit into this goal? I'm here, right, in this group. Plants and forests are going to pull carbon out of the air. Anytime we can promote more plant growth, more forest growth, we're going to be pulling carbon. So continue to support that. More photosynthesis, more organic matter in the soil, particularly local biochar and compost. Keeping the soil covered. Always have a plant. Always have something growing. Which native plant should I plant? Well, this is where we're going to do our citizen science, right? We should plant things, test them, and make observations, right? Because when we look at future predictions, we're going to see that some species are probably going to do well. A northern red oak is going to do well in a warmer climate, particularly in this area. Eastern white pine actually is going to do worse, likely. So we can think about which plants we want to plant or support based on kind of what they're going to look like in the future, in a warmer climate future. Where to source these things based on the types of emissions that happen, we're probably going to be sourcing new plants from regions where they have been adapted. And what I mean by that is that if we are looking to plant in Western Maryland under a curb emissions now scenario, we could start sourcing plants that were adapted to middle West Virginia. right? Whereas if we don't curb emissions now, my Frostburg, when I lived in Frostburg, I should be sourcing plants that are adapted to northern Tennessee, right? So thinking about kind of when if we're regrowing or an individual scale doing landscaping, thinking about where we're sourcing that from is important to think about relative to our future climate change. The last thing I'll end with, y'all, is I also know I've been talking a lot about carbon, and I know that I can get carbon tunnel vision. The scientist in me loves talking about one thing and nerding out about it, right? But there's so many other things that matter, right? Carbon emissions is just one piece. We have water, poverty, air pollutants, inequality, overconsumption, education, biodiversity loss, all important things as well. And they're all connected together, okay? So I don't want to necessarily lose sight of these other priorities. Carbon emissions is just what I love talking about, but these other priorities are important as well. My takeaway, there's no silver bullet. We know the solutions. We have the technology. Implement it more. That's the solution. All right, y'all.
Presentation.
Yeah, I'll take any questions, y'all. Any thoughts?
Yes, I have again.
Yeah.
So you address transportation
Yeah.
going down, more electric vehicles.
That's right.
We addressed electricity,
Mm-hmm.
solar, wind.
Mm-hmm.
What about industry?
Yeah.
It's a big player.
Good question. Yep. So I think that industry, one of the things you saw on there with like the 6 things that I told you to look at from that Berkeley group, one of those things were building efficiencies and heat pumps, which will impact industry in terms of thinking about the infrastructure that they have. And so that is one way to decrease it. That honestly, that's been the trickiest one for me to figure out how to come up with like real tangible solutions, current tangible solutions. Of course, there's regulation that can be used to try to implement carbon tax measurements or carbon tax proposals that essentially industries are going to adapt in order to reduce the tax burden if we did a carbon tax in the US. So that's one proposal that I've looked into and read about, but yeah, for sure. Yeah. And that gets into just electricity generation in general, but yep, you're right. Yep.
Jake, we've had a question about whether the slides could be made available. I've let them know that it will be, the Zoom program will go on the BRNN YouTube channel in a week or 2.
Yes, I can give you the PDF of the slides, no problem.
Any other questions here in the room?
I have read that. Thank you. I've read that a lot of the electrical vehicle charging stations, especially Electrify America, are backed up by green energy. Is that really true? He's grimacing.
Yeah. A bit mixed. A bit mixed. Yeah, I've looked into similar things where I've seen examples of electric charging stations that were fully renewable. But then I think I've probably seen more of they are backed up by the fossil fuel energy. So at the same time, you know, there's a balance of that. There's a balance of the need for the reliability of the charger itself, right? You could pair that with a battery, right? And essentially you're just going from one battery into your car battery, right? One battery to another. So that would be one way to kind of avoid that fossil fuel charge, of a fossil fuel electricity charge. Um, so yeah, I would say I'm not sure I can give you much more than the data that I've seen. I've also shown it being mixed as well. So
But there's still the difference between point source pollution and non-point source pollution.
yes, yeah, definitely.
Well, if no more question, let's have another round of applause. This was a wonderful presentation.
Thank you all for your time. I appreciate it. Always enjoy talking about carbon emissions.